This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Today's speaker, I think we're all familiar with at least the products of what he's done. Computer science is a fun field because it's sort of new. Not only can we stand on the shoulders of giants, but we can step on their toes. And if you, it's not a threat. If you walk around Stanford, you'll see a lot of names on buildings. There are basically two ways to get your name on a building. One is to buy it. And, you know, that works. The harder way to do it is the way today's speaker did it. He did something amazing. He basically invented all the, with Robert Kahn, invented many of the protocols that underlie the internet today. Then he did something harder. He got them adopted. And those of you who have worked in large organizations know how hard it is to do anything in a large organization. He managed to do it across organizations. And this is an amazing feat. It doesn't happen. The internet, and I mentioned it was a stopgap, and all the competitors are now dead. Those of you who have been around way too long remember that Margaret Jackson was going to be wired for DECnet. When's the last time anybody saw DECnet? With that, I think it's just time to go and let him tell us where it's going and where it's been, and how come, even though the RFC for interplanetary TCP/IP is 5 years old, we're not talking to Mars?
Thank you very much. I'll try to answer that last question.
Thank you.
Well, thank you very much for coming. I assume that not everyone is enrolled here for credit. This must be either that or this isn't a class, it's a happening. My task this afternoon is to try to give you some sense for what's going on in the internet. Now, you're using it all the time, so you surely already have a pretty clear sense of some of the things that are going on. But I'm going to try to pick on a few things to dive into a bit. And one of the things I'm going to pick on is areas for research. These are things which are not solved problems, could probably require some significant re-engineering of the internet protocols. And that's an area where I hope some of you will be able to make some contributions over time. Let me start out, as I always do, explaining my title. I'm Chief Internet Evangelist at Google. Now, I know this seems a little funny, but in fact, what you see are the academic robes of the University of the Balearic Islands. So this is a legitimate, fully garbed academic regalia for that university. I got an honorary degree, and they let me keep this outfit. And I have to say, you don't often find a place and time when you can wear something like this. And when I went to work for Google in October of 2005, they asked me, what title do you want? And I said, well, how about Archduke? Which I thought sounded pretty good, but they reminded me that the previous Archduke was Ferdinand. He was assassinated in 1914, and it started World War I. So maybe that's not a good title to have. But they said, considering what you've been doing for the last 35 years, how about being our Chief Internet Evangelist? So I thought I would wear the most ecclesiastical outfit that I knew or had on my first day of work. So Eric Schmidt took this picture. Let me just remind you of some statistics. 10 years ago, I would have been very excited to tell you that there were 22+ million machines on the internet and 50 million users, which at the time seemed like a big number. Today, it's almost 500 million machines on the net that are servers. So they're things that have domain names typically and at least dedicated IP addresses, as opposed to laptops and personal digital assistants that are connected episodically. and over 1.2, almost 1.3 billion users. That's still a small number relative to the world's population. So we are still, the Internet Evangelist has another 5.5 billion people to convert over to Internet operation. The other thing that's been going on during that same 10-year period has been a rapid influx of mobile technology all around the world, particularly in places where there was very little telecom infrastructure. The reason that that's important from the Internet point of view is that more and more of those devices are now becoming Internet enabled. The rough estimates I have heard are that about 15% of the currently operating mobiles have some form of Internet access, whether that lets them surf the net using search engines like Google and others, or interact with some other application. That 15% translates into about 450 million additional devices on the net. And if you add the laptops and other things, you could very quickly convince yourself that there are on the order of 1.5 billion or more devices already on the Internet. That's more than there are people. And of course, that suggests that some people have more than one device that's Internet capable. Maybe you have a laptop and a mobile as an example. Over time, I expect that's going to, that ratio of number of devices to the number of people is actually going to increase, and I'll give you some examples of how that might happen. If you look at the distribution of users on the Internet today, you discover some interesting facts that are almost inescapable trends. The first one is that it's Asia that has the largest single block of users. Now, of course, that's a very diverse region. It includes China and India and Indonesia, Japan, and so on. But the implication is that with only 12.4% penetration of the population of Asia, with a number like 460 million, by the time they reach the same kind of penetration rates as we have in North America, there are going to be a lot more Asian users on the Internet. That implies that the content of the network, the style of use, the kinds of interests, the modes of operation in that group will influence much more heavily what's on the net than what you might see today. So we need to be prepared for that if we're interested in offering products and services to a global population. That's going to be an important target. Europe is the second largest grouping, and Europe is sort of funny, right, because they keep adding countries, so you can't quite make much in the way of predictions about how many people they're going to be. But on the average, they're only 43% penetrated. And yet they are number 2 on the list. Of course, the dynamic range of penetration is quite strong. I mean, there's 70% penetration or more in places like Sweden, Norway, and Finland, and then some of the southern countries you find are more like 5% penetrated, but the average is 43%. And North America is here with a high penetration rate, 70% plus in US and Canada, which means that our absolute population of Internet users is not going to get much bigger because our total population in North America is only on the order of 320 million or so. The implication, in a sense, is that the history of Internet up until now has been very much influenced by North American interests and content. But over time, it's very clear from these data that that will change, and that we are already in the minority in terms of absolute population. The last item on the list here is Africa, and I guess it has clearly very, very low penetration right now. There are about 1 billion people living on the African continent, and so only 42 or 44 million are thought to have Internet access, and it's very spotty. You'll find a significant amount of penetration in relative terms in South Africa, for example, in Egypt, in Morocco, and Tunisia, but in sub-Saharan Africa, it's very, very limited. That statistic, however, is going to change, especially as more and more people in Africa get mobiles that are Internet enabled. That's probably been the strongest growth of telecom infrastructure in Africa. The wireline growth has been almost de minimis. They've leapfrogged over and are heavy, heavy users of mobile as an alternative. Just for fun, I thought we'd leap back into history and look at the December 1969 picture of the ARPANET, this predecessor to the Internet. And there were only 4 machines on the system. And I had the good fortune to be a graduate student at UCLA programming the Sigma 7 to put it on the ARPANET. So,
do you want your original slide, though?
You have it. Oh my gosh, look at this. Look at this. Where did you get that?
Postal?
Wow, out of sight. There it is. Whoops, here we go. we got to zoom in on that. Now, you can't see it that way, can you? That doesn't work. Thank you. Now, that Sigma 7 is in a museum now, and some people have suggested I ought to be in there along with it, but somehow I've avoided that fate, although the Computer History Museum isn't very far away. This is what the first packet switch delivered to UCLA looked like. It was called an Interface Message Processor, or IMP, and it was delivered in a very heavy metal container. The people that built it, Bolt, Beranek, and Newman, are in Cambridge, Massachusetts, and they knew that this was a military contract. They had 4 of them to deliver first to the 4 nodes you just saw, and they weren't quite sure exactly what they should do given that it was being delivered under a Defense Department contract. So they delivered it in this heavy metal box with screw eyes in the top that would let you lower it down from a helicopter in case you needed to install it that way. Of course, it ended up, the first one ended up at UCLA surrounded by undergraduates and graduate students, which means that the heavy metal container was exactly the right idea for that environment. Now, when the contract was awarded to Bolt, Beranek, and Newman in Cambridge, Mass., they got a nice note from Senator Kennedy, who said he congratulated them on their ecumenical effort in building an interfaith message processor. So they thanked the senator for his good sentiments. Some of you will have been to the Computer History Museum. Some of you may even have been to a recent celebration, which I'll tell you about. This was a mobile van that was built to test packet radio in the San Francisco Bay Area in the 1970s. ESRI International built this. They were responsible for assembling and demonstrating mobile data communication. Now, the Defense Department had successfully demonstrated the ARPANET publicly in October of 1972 and showed that packet switching as an interactive means of computer communication was a very successful technology. But then they said, well, if we're really going to be serious about doing command and control and using computers, we better make sure we can put them everywhere that they have to go. Well, that means in militarized vehicles and tanks and so on. And you can't drag wires behind these things because the tanks run over them and the wires break. So that's not a good idea. You need mobile radio. And for ships at sea, you need satellite communication. So for the packet radio network, this van was put together in order to test the system in live operation up and down the Bayshore Freeway. Inside were these $50,000 cubic foot packet radios transmitting at 100 or 400 kilobits a second using spread spectrum technology. Now, considering this is in the mid-1970s, that was a very advanced concept for its time. The system also was used to test packetized voice. So people who think that voice over IP is a recent development, you might even think 1996 was recent when Vocaltech in Israel released one of the first commercialized voice over IP packages. This is really 20 years before that. Now, I have to tell you that one of my favorite anecdotes about testing packetized voice, because the packet radio net, although it was carrying traffic at 100 kilobits a second, burst rate anyway, the ARPANET was carrying its traffic at 50 kilobits per second. That was the backbone capacity of the ARPANET. Not even 56 kilobits, it was 50 kilobits. And so, well, a normal voice channel is 64 kilobits, so you can't cram a whole lot of voice down a 50 kilobit channel. So what did we do? We said, well, maybe we can digitize it and compress it. So we did. We used what was called linear predictive code with 10 parameters, a stack of cylinders that modeled the voice tract whose diameters changed as the speech was formed, and the whole stack excited by a formant frequency. You transmitted only the formant frequency and the diameter of the cylinders to the other side, which then undid that computation and produced sound. Well, you can imagine that you lose a certain amount of quality as you go from 64 kilobits a second to 1800 bits a second, which is what the LPC-10 produced. And what it effectively did is make everyone who spoke through the system sound like a drunken Norwegian. So the day came when I had to demonstrate this for the military, and I remember thinking, okay, how am I going to do this? Then I remembered that one of the participants in this program of packetized speech was from the Norwegian Defense Research Establishment. Perfect. So we set up this demo with Ingvar as the speaker. So first he spoke through the ordinary switch telephone network, and then he spoke through our system, and it sounded just like him both ways. Perfect. Of course, we didn't tell the generals that everyone would sound that way. It was understandable speech, though, and very important. So the fact is that we were experimenting with some of the ideas that are common today in a small scale. This is the packet satellite system. We used Intelsat 4A over the Atlantic. We had multiple ground stations all competing with each other for shared channels on the network. So a single channel up, single channel down, people essentially potentially colliding with each other, trying to transmit. So we used what was called CPOTA, which is Contention Priority Oriented Demand Allocation of the satellite channel. You basically had a period of time when you transmitted your requirements, and if you didn't interfere with anyone, everyone would hear the requirement from the ground station. If you collided, nobody would hear it. So you basically transmitted your requirement in this aloha mode, and then waited to see whether or not your requirement came back down again. If it did, you assumed everyone heard your need. And then after this period of contention of announcing requirements, then you went into a scheduled period where everybody computed the same schedule based on the information that they had all gotten. Sometimes you get out of sync and you had to have mechanisms for detecting that and shutting up until you figured out that you knew what the schedule should be because you were not the party contending. But it actually worked pretty well. So each of those different networks, the ARPANET, the Packet Radio Net, and the Packet Satellite Net, were developed in this same general time frame. But then came the day to try to demonstrate that we actually had a technology that would link all three of them together. Now remember, they're operating at different speeds, different packet sizes, different error rates, different delays and round trip times. And yet we wanted them all to look uniform. And that's what TCP/IP and the Internet architecture was all about. So on November 22nd, 1977, we demonstrated this three-network test. And this is what we celebrated at the Computer History Museum last November, was the actual demonstration that the three networks would work together in this uniform way. Now, if you look at the path here, you'll see that there's a packet radio van that's driving up and down the Bayshore Freeway, transmitting data ultimately to USC Information Sciences Institute in Marina del Rey, California. So the basic transmit path is 440 miles or so. But the packets didn't go that way. The gateways, we call them routers now, but we didn't know that, so we called them gateways back then. The routers were, or the gateways were programmed in order to force the traffic out of the packet radio net into the ARPANET, all the way across the ARPANET through an internal satellite channel of the ARPANET that reached all the way over to Norway, and then down to a landline, through a landline to University College London. And then out of the ARPANET at that point into another gateway and into the packet satellite net, back over the satellite, synchronous link, down to Etam, West Virginia, then back through another gateway into the ARPANET again, all the way across the ARPANET and down to USC. And so the actual packet path was on the order of 100,000 miles one way because of the two satellite hops plus back and forth across the Atlantic in the United States. Well, much to our amazement, it actually worked. And I don't know, those of you who deal with software will appreciate that most of the time when you try stuff out, it doesn't work. And so I was leaping around screaming, it works, as if it couldn't possibly have worked, but it did. And I was so happy that we were able to show that three networks would interwork together that I drew this picture and had it framed, and I sent it up to the then director of ARPA, who was George Hallmeyer at the time, to say that he hadn't wasted all of his money on a demonstration of this type. Sir?
What was the latency through this thing?
Oh my God. The latency was probably on the order of, if you do just the round trip times, right, you're a quarter of a second up and down, another quarter of a second up and down, another quarter of a second up and down, another, so it's a couple of seconds at least. Yeah. And plus, you know, there's some store and forward delay too. So we were lucky, we were probably getting a grand total of 2.5 to 3 packets a second with a, you know, round trip time of about 3 seconds. You know, wouldn't really work well for a video game, bang, bang, shoot 'em up. Okay, well, if you fast forward to 1999, Bill Cheswick, who was putting these beautiful charts together showing how the internet was interconnected. The thing that's highly connected up at the top, I think, was the UUNet backbone, which had a lot of connections to many different networks. So you get the impression that the internet got bigger, it got more complicated, it got more connected, and it got more colorful, and I think that's as good a description of internet as anything else you could come up with. Okay, so how do we get where we got? On this campus in 1973, Bob Kahn and I wrote the first paper, which was published in 1974, describing what the internet would look like. And one of the things we decided up front was that we did not want this net to be superannuated by some new transmission and switching technology. So we said the internet packets should be essentially insensitive to how they're being transported. So this led to the idea that we should try to make the architecture completely agnostic when it came to whether things were transmitted over fiber or satellite or store and forward underlying networks or anything else. So I had a t-shirt made that said IP on everything. And that was my mantra, was to try to make sure that the internet protocol would run on any new transmission and switching system that came along, and indeed that's exactly what happened. The other thing, though, that I didn't fully appreciate at the time is that the packets not only don't care how they're carried, they don't know what they're carrying. The network is essentially unaware of the applications that are running through it. That turned out to be a fortuitously good decision, because it meant that you didn't have to get permission from anyone and you didn't have to alter the network in order to try a new application. Only the computers at the edges of the net knew how to interpret the packets. So the result is what we call the end-to-end principle, and that has driven a huge amount of invention and creativity in the internet over the ensuing decades, because nobody had to go and get permission from an ISP or to get them to alter the network in order to test a new idea. So when Larry and Sergey left Stanford to do Google, they didn't have to get permission from someone to try that out, nor did the guys who started Yahoo or Amazon or any of the other companies. They simply put up these new applications, and since the net was essentially neutrally transparent to the application, anyone could try it out. Obviously, radio has become increasingly important now because of the mobile use of the internet. And broadband is becoming important because there are things you can do at high speed that you can't do at low speed. There is an issue in the United States right now with broadband, several issues, but one of them is that the services that you get are not symmetric. So the data rates that you can get are typically high data rates coming in from the net and low data rates going out. The side effect of that is that you have an anomaly where you could receive fairly high quality video, but you can't send it. So if you and your buddy are both on broadband services, you still can't get very good quality video back and forth. I think that that is an unsatisfactory condition, and that consumers are going to start complaining that they can't get the kind of service that they can get in other parts of the world. So by way of example, in Japan, you can get a gigabit per second service, full duplex, for 8,700 yen a month. And it was demonstrated to me when I was in Kyoto a couple of years ago. Or if you happen to be living in Stockholm, you can get dark fiber for about 100 euros a month and put your own electro-optics on it. So there's an engineer from Cisco, Peter Lothberg, whose mother has an OC768 connection to the internet, 40 gigabits per second. I have no idea what she does with 40 gigs. To be honest, I have this awful thought that there's this optical fiber that's going somewhere and she's hanging the laundry on it, but that would be, you know. Now, there's another issue which is upon us. In fact, let me go to the next chart. I think I have it here. This, forget all the lines and just look at the one that's going down. That is the remaining space available in the IPv4 address space for ICANN to allocate to the regional internet registries, who then allocate it to the ISPs. In fact, the current estimates are that we will run out, or ICANN will run out of allocable IPv4 address space somewhere around 2010, maybe the middle of 2010. Now, that doesn't mean the internet will come to a grinding halt, but it does mean that if we need more unique address space, we need another address space to do it. And so 10 years ago or more, a standard was developed called IP version 6. It has 128 bits of address space. If you do the math, it's 3.4 times 10 to the 38th addresses. I actually made the mistake of running around saying that meant every electron could have its own web page if it wanted to, until I got a note from a guy at Caltech, "Dear Dr. Cerf, you jerk, there's 10 to the 88th electrons in the universe and you're off by 50 orders of magnitude." So I don't say that anymore. In some of you, if you're counting, you might ask, what happened to IP version 5? Because you're using version 4 now, and the answer is we actually had a protocol different from IPv4 that was trying to do streaming audio and video, but it did it in a way that wasn't very scalable, and we abandoned it. but we didn't want to reuse that protocol ID to avoid any confusion, so the next one was IPv6. So I am pushing very hard wherever I get the opportunity, including here, to say that we really need to take this seriously. We need to get busy to implement IPv6. For the most part, software in the servers, software in the laptops, and software in the routers are already available to run IPv6. And I don't mean to suggest it's just a question of turning it on. There are, it's not a not trivial exercise to do that. However, the internet service providers are not offering the service, and they're saying, understandably, nobody is asking for it. This is sort of like the hole in the roof where it's raining, so you don't want to fix it while it's raining, and when the sun is shining, it's not a problem, so you don't bother. So, right. So anyway, we have a problem, which is to convince the ISPs that there is a market for IPv6. And I hope that I'll be able to help stimulate that thinking over the course of 2008, because I think it will be some time, take us some time, to actually implement and test IPv6, get connectivity among the v6 operating regions. The problem, as I see it today, is that there are places that can and do run IPv6. In China, for example, there's a whole national scale research network, 10 gigabit system running IPv6, operationally. You don't see that in very many other places, but you do see it there. The problem is that when the original internet was designed, new networks were connected to an already connected system that had full IPv4 connectivity. But the v6 stuff is sort of popping up in an erratic way, and just because you're running v6 does not mean you're connected to somebody else that's running v6. And so there is an issue here about maintaining connectivity in both protocol bases, and that has to be addressed. Hello. Okay, so I promised that I would spend a little time talking a bit about research problems. Let me preface this by observing, first of all, that the internet stuff has been around for 30 plus years. That does not, and we've had experience with it in a fairly large audience, so to speak, certainly in the last 10 years, with 50 million and now 1.2 billion users. But there are still things that are not satisfactory about the design and the architecture. One of them very clearly is that security is a big issue, and it's a big issue at many different levels in the system. Whether it's denial of service attacks that are hitting you at the IP layer, or viruses and worms that are arriving through a browser and then infecting your laptop and turning it into a zombie, which is now managed by a botnet herder who is handing out his botnet 10,000 or 100,000 or whatever units to generate spam or to generate denial of service attacks or to do other kinds of malicious things. It's there, and it's sort of disappointing in a way that you have a system that has this great positive potential and somebody has figured out a way to interfere in some fashion with it. But that's the real world. Once you get the real, the general population up on the net, you get virtually in the network every deficiency and every positive thing about the society is reflected in the network. We don't understand the statistics of the net very well. The core of the net, when you look at the backbones, because they aggregate so much traffic, actually have some fairly predictable statistics. The law of large numbers is helping us there. But at the edges of the net, you see extreme variations in the demand. It's not too surprising. You might be clicking on a mouse a little bit, going from page to page to page, and all of a sudden you click on a file transfer and you've got 100 megabits a second coming at you. So the ability that Erlang had to talk about the statistics of the telephone network were far more easily derived, because all they really were doing was nailing up a 64 kilobit channel when it was digital. Before that it was an analog link, and somebody spoke, and that was it. So typical 3-minute conversation with some kind of a bell-shaped distribution, that was all. And so his statistics for utilization of the telephone net were readily derived and very, very helpful for planning and provisioning of telephone network services. Internet has this huge dynamic range, and to make matters worse, every time you turn around with a higher speed service, somebody invents another way to use it that you didn't think of, which has yet different statistics. So we don't have good Erlang formulas to tell us about the edges of the net and how to provision them. There are huge debates about quality of service. Some people say you don't need it. Some people say it's essential. And I actually, for quite a while, I found myself on alternate Tuesdays with different opinions, going back and forth. You know, one scenario said, okay, we don't have infinite resources. We want some things to have low latency. We have other things that need to be, you know, to have high bandwidth. And we need to configure the system so that it actually delivers different kinds of performance. But as soon as you start going down that path, you say, okay, but if I do that, I wonder if I shouldn't charge people more for the high capacity or more for the low latency. So right away you start thinking, oh, now I have to start keeping records of how much of each kind of service did I offer. Well, in the telephone world, there are things called call detail records. I used to work at MCI. We collected 90 terabytes of call detail records a month in the system, and that was 10 years ago, so I'm sure the number must be bigger. And you needed it in order to generate the bill because you were charging based on time and other parameters. So as soon as you start looking at that and you think, holy cow, if I start collecting that kind of data from the internet, I'm now, not only do I have a lot of data to move around, but I have to process it. So now I need big iron and or large numbers of processors, and that's going to cost money. So then you start thinking, well, wait a minute, what if I took all the money that I was going to spend on doing all this QoS collection and analysis and spent it on putting more capacity into the net? Then everybody gets better. And so, I would go back and forth like this. I have to be honest, I'm really still of the opinion that we should just keep increasing capacity because we certainly haven't run out of the ability to jam more stuff down a fiber, for instance. But the debate continues. I honestly do not have time as I look at the clock here to go through all of the list here, but I want to pick a few more out which are particularly interesting and potentially attackable. Mobility, even though we had that packet radio system, the mobility was confined to within the radio range of the system. But now we have people running around with mobiles. They connect and disconnect to the network. They could be connected in New Delhi and then a few hours later they're in New York. And so their appearance on the network is by no means continuous. The notion of handoff doesn't make a lot of sense in the context of disconnecting, getting in an airplane, flying somewhere and reconnecting again, maybe getting a new IP address. The internet protocols are not very friendly when you go around changing your IP address. It causes the TCP connections to be essentially destroyed and they have to be reconstituted. The application layer has to be aware of these things. We could do a much better job of mobility, but in order to do this, we need to have another layer of identification which is independent of the underlying IP address. The IP address is telling you how is this being connected to the net, at what point? At what point am I literally connected to the net? A higher level identifier could be something which is bound and rebound to different IP addresses, maintaining the TCP connections. You might say, well, aren't domain names that? The answer is not quite. The domain names offer a different kind of persistence, yet another higher layer of protocol. But if we invented a new class of identifier that could be bound and rebound to new IP addresses, that would give us a better handle on continuity and reconnection. Now, the obvious problem is that also opens up an opportunity for hijack, because you could, someone else could say, hi, my IP address changed and here I am again. And of course, it's not you, it's just someone else who wants to steal your connection. So now we need to have authenticity and strong authentication using some cryptographic means. So we don't have time to go through all of this, but this ability to maintain connections over disconnect and reconnect is an important thing. The other thing, which is at yet a higher level of abstraction, has to do with processes. There's a lot of what goes on in the internet is inter-process communication. Imagine, for the sake of argument, that two processes are interacting and then one of them goes away, is disconnected for an uncertain period of time. That period of time is sufficient that the operating system that was running that process has been rebooted a few times before the process comes back up again, and then the other guy shows up, and suddenly you receive a communication from a process that had been talking to you 2 weeks ago. So the question is, well, do I have any way of recovering the state that I was in when I sent the, an exchange out to this process, which suddenly was reincarnated and sent something back? I think there's a lot that we can do in that domain to create a highly resilient system. Multihoming is another place where we have a problem, and again, IP addressing is the source of the difficulty. When people want high reliability, they plug into two ISPs, but typically they end up with two different IP addresses. And this is kind of unfriendly. There is a possibility to get what's called provider-independent addressing, but you have to persuade the ISPs to put that address block into all of their global routing tables, and not all of them are willing to do that. So We don't do a good job of multi-homing either. When we pick paths in the network, we often pick a path after trying to sort out what's the minimum path or what's the highest bandwidth or lowest delay. But the thing is, we only push the traffic over that one path until some parameter causes us to choose a different one. Well, wouldn't it be interesting if there were multiple paths between the source and destination, if we could push traffic on both of them or three of them in order to increase the total capacity between the two? We don't do that. What about broadcast? What do we do today? What we do is we take broadcast media and we turn them into point-to-point links. Well, you know, in some sense that's dumb. And we have not designed the protocols to know that they're operating in a broadcast medium and take advantage of it. For example, if you wanted multiple parties to receive the same information, if you knew you were on a broadcast network, you could build a protocol that knows that, transmits the data once. Yes, some people won't get it, and maybe there's local noise or something, and you have to have a recovery mechanism, but you could send huge amounts of data to large numbers of targets in much more efficient ways if you knew that you were in a broadcast environment. So we don't do that very well. Okay, so I'm not going to go through all the rest of these, but I do want to say that there are yet other problems, some of them not in a technical space, that need attention in the internet world. I alluded to authentication. It's a major weakness in the network that today you can't quite authenticate the source of the traffic that you're receiving. That has led to all kinds of abuses, including faking of the source IP addresses of packets as part of a denial of service attack. It would be nice to be able to say, please tell me who you are, or at least confirm that the host that is asserting this IP address, in fact, is the one to which that address was assigned. That, once again, gets into some sort of digital signature exchange. And even if you have an identity, it doesn't necessarily tell you what that identity is authorized to do. And I'm sure a lot of you have bumped into this if you're doing any kind of operating system design, any kind of time-sharing systems or service systems where you need to know something about the party, like, is this a paying customer or not? That's sometimes a very important question. Some of you, I hope, have been noticing that the design of hardware has reached a rather interesting stage where we are not seeing increases in the clock speed of the processors. Now, I'm a software guy, so I'm going to try to say what I think is going on here, but I may be wrong, and maybe you'll help me with this. But my understanding is in order to increase clock speed, you often wind up having to increase the power levels that you drive these things at, and that generates more heat. And at some point, you get to a stage where it's too hot and the thing melts or it does some other bad thing. And so in order to cope with that, the designers are putting in multiple cores on a chip, running each of the cores at a rate which does not exceed the heat dissipation limits. But this poses a problem, several in fact. First of all, you got this chip, and the I/O capability on the chip may not have increased even if you have multiple cores on it. So now you are sharing among multiple parties the I/O bandwidth of the chip. The second problem that you run into is that the algorithms that you're running, which you used to be able to run serial algorithms and rely on Moore's law to say, I can run them faster because the chip clock rate got higher. Now you don't have that benefit, and in order to achieve the same throughput, you may need to parallelize the algorithms. And there are some algorithms that don't parallelize very easily. And so for some applications, the multi-core processor poses a real challenge in algorithm design that we otherwise have had the luxury of ignoring in the past. Another thing which is a major issue for the present internet architecture is that it is not very tolerant of high delay and is certainly not very tolerant of disruption. TCP connections time out, other kinds of connections, they're not necessarily TCP connections, but links that are UDP links that are maybe carrying streams and things like that, eventually time out and you lose the connectivity. Most of the algorithms that we've designed have built into them an assumption of low latency. And that assumption doesn't always hold. It also assumes that most of the time things are connected. That doesn't always work either, and especially in hostile radio environments. So, assuming I manage to get there in time, I'll mention an interplanetary architecture which deals with delay and disruption, but whose results have been mapped back to terrestrial applications where we have a lot of disruption and uncertain delay. I'm just going to say that intellectual property protection, one of us in one earlier, before we started the conversation about this problem of intellectual property, it was Geo Weirderhold brought this up. This is a huge issue now because once things are in digital form, it's easy to replicate and distribute them. And that's different from the history of most intellectual property controls, at least copyright, dealt with physical objects. And it was hard to reproduce those and distribute them. It was costly. But bits don't cost much to reproduce. They don't cost much to transmit. And so figuring out what the right intellectual property regime is in this digital environment is turning out to be a challenge. Somebody has to deal with that. Lawrence Lessig here at Stanford has done a nice job of crafting at least one different idea called Creative Commons. The governance of the internet has raised huge debates from country to country. There are a number of countries around the world who believe that the Department of Commerce controls ICANN and that ICANN, the Internet Corporation for Assigned Names and Numbers, controls the internet. Well, I used to be chairman of the board of ICANN until the end of November last year, and I guarantee you I did not control the internet. And I can also guarantee you that the Department of Commerce didn't control me either. But the fact is that people wonder what the rules should be. There are lots of things to be concerned about. Abusive behavior in the network, child pornography, all the, fraud, creation of business environments in which you can authenticate the parties so that when you do a contract of some sort, you have some belief that you can reinforce it. You can enforce the terms and provisions of this electronically signed object. There are lots and lots of issues there, methods by which policy is developed, the parties involved who make the policy, mechanisms for enforcing it, all of those are in play right now. And they have a lot of political overtones that are outside the bounds of the internet itself, but often have to do with the attitude that one country has for another and its policies. Okay. Another thing that I think is important to recognize is that the internet, as it grows more and more people, is exhibiting behaviors that I certainly didn't predict. One of them is that most of the consumers of information have now become producers of information. This is different from the original notion of mass media, where there were a small number of producers and a large number of consumers. But now with things like web pages and blogging and video uploads and things like that, a huge number of people are now producing content on the network. Innovation in the net, especially in the production of content, is barrier-free. And perhaps the best illustration I can give you of that is, imagine you're looking at a paragraph of the Wikipedia, and you see a word in this paragraph that you know is wrong because you're an expert. So you go in and you change that word. Now, you wouldn't publish a one-word paper, and you wouldn't publish a one-word book, but you can reasonably publish a one-word edit to a Wikipedia entry and actually make a significant contribution. Of course, the net will also accept a book or a scholarly paper or a movie or any other digitizable object. So this barrier to offering content is really at zero. There are no boundaries at all. We're seeing a lot of, especially young people, getting excited about social networking. So things like LinkedIn or MySpace or Facebook or Orkut and so on are all very popular, along with game playing. And the thing that makes the game playing interesting is that it is participative game playing. People are actually interacting with each other. They're not just playing against a computer-driven simulation. So the people who play the games, in fact, use the net not only to play the game, but they talk to each other while they're playing the games. And you have to in some of these games, where you're shooting at somebody, you don't have time to type on a keyboard, and all you can do is holler, get out of the way. So people are using the high-speed net, especially, for very low latency, very interactive environments. And if you look at Second Life and World of Warcraft and some of these other things, these are amazingly complex sociological phenomena. They're so interesting that I've been told that there are economists, maybe at Harvard, who have assigned their students to go in and become participants in Second Life in order to observe the economic behaviors of the characters that are in the game. Business models are being turned on their heads by the economics of digital everything. And the best illustration that I encountered of the dramatic reduction in the cost of doing anything digital was recognizing what it cost me to buy 2 terabytes of storage for use at home. A few months ago, it was $600 for 2 terabytes of storage. And I remember thinking, back to 1979 when I spent $1,000 for a 10 megabyte disk drive. You know, and it was the size of a shoebox. This got me thinking, I wonder what would have happened if I tried to buy a terabyte of disk storage in 1979. Well, if you do the math, it's $100 million. Now, look, to be honest, I didn't have $100 million in 1979. And actually, I don't have $100 million now either. But if I had had $100 million in 1979, I guarantee you my wife wouldn't let me spend it on disk storage. I'm sure she would have had a better idea. But the dramatic reduction in the cost of processing, storage, and transmission of digital information is so extreme. I mean, we're talking factors of 1 million or more, that business models that were based on older technologies and costs are in fact having the rug pulled out from under them and have to be completely rethought, and some of them may not survive. This is a Darwinian situation. Darwin says you only have two choices, adapt or die. And so companies are going to have to adapt to the reality of the new economics. Okay. This is just a little illustration to show how quickly a particular application can take up a significant fraction of internet capacity. This sort of gray-looking thing that says YouTube shows the diurnal variation of bit rates at the edges of the net at the place that Sandvine was measuring for a variety of different peer-to-peer and other applications. And it's pretty clear that YouTube, which is only a couple of years old, had become sufficiently popular to use up a substantially visible fraction of the access capacity of the net. I'm told by the YouTube guys that something like 8 hours of video per minute are being downloaded into the network today as part of their service. Well, that leads to another observation about the side effects of video in the internet environment. A lot of the internet service providers, particularly the telcos, are focused very, very much on streaming video. So when you say IPTV, they're thinking just delivering video packets at a rate sufficient to watch it. And I suggest to you that that is too narrow a view of what you can do with IPTV. There are two parameters. One is whether or not you have high enough data rate to deliver streaming video in real time, or a sufficient capacity to store a substantial amount of video and then play it back in real time. If you have no storage and you have no ability to transmit the video at consuming rates, then nothing works. It's not a useful environment for video. If you have a very high transmission rate and no storage, every kind of video you produce, whether it's real-time video being produced in real time, like a news show or maybe a sporting event or something, you can deliver that essentially in real time. If it's pre-recorded, you can still deliver it in real time. In fact, if you have a high enough transmission rate, you can deliver pre-recorded material faster than real time. That's what the iPod people do when they download music. They download the music faster than they would listen to it. Then they play it back whenever they want to. Well, this is a form of time shifting. And I believe that we are going to see a lot more of that kind of time shifting and downloading of content faster than real time as the data rates at the edge of the net go up. Well, that leads to some very interesting behaviors. One of them is that if you download a file, because you're not watching it while it's downloading, you don't have to worry about whether every packet gets there exactly on time. They don't even have to get there in the right order. You just have to get the file. And in fact, if you get enough of the file in the right order, you can start playing it back after you started the download. You don't have to wait for the whole thing to be downloaded before you can play it back. In fact, you see a lot of that in the short videos on YouTube. You can see that you're starting to see the video coming well before the total download has completed. But the thing I wanted to point out is that there are business models that are lurking inside of this notion of being able to download stuff as a file transfer and then play it back later. If you think about packet stream coming at you, since the packets are insensitive to their content, if you download what would normally be thought of as an entertainment video, it could contain not only the video and the audio, but all kinds of other information. It could be a program, it could be text, it could be the biographies of the actors and the director and so on. It's anything that can be digitized. What makes that interesting is that when you're playing it back, you're playing it back through an object which is programmable. So it's not a dumb raster scan device. There's software that's interpreting the packets that you downloaded as a file. Some of that file could contain advertising information. Now, before you say, oh crap, we're back to, interrupting the action at the crucial moment and another commercial comes up, it doesn't have to be that way. because the programmable device can decide, well, let's see, I'm going to use a little bit of the screen for some buttons to push if you're interested in what you see in the field of view. You know, stop the action, tell me about this car or this, you know, this particular outfit or anything else. Or you could even sensitize some of the objects in the field of view and mouse over them and click on that. So the ability to interpret the bits in a way that's different from the traditional raster scan presentation of video opens up an opportunity for advertising that's very interactive. Now, I don't know whether that will work or not, and I want to be careful to tell you that this is not a Google idea that we're pursuing. This is just Vint Cerf speculating, so I don't want you to run out of the building and say that Google is doing interactive video advertising, because I don't know if we'll conclude that that makes any sense at all. Some of you may figure it out and do it on your own. But the idea that you can present information in a much more interactive way, leaving the users in much more control over their entertainment content or other information content, is the point. Okay, so I'm going to skip forward here to a couple of other slides, and then I want to get to some Q&A. This one is, this is my personal surprise over the years at seeing people connect stuff to the net that had never occurred to me that you'd ever want to connect. Now, we used to make jokes about ToasterNet, and somewhere around 1989, somebody actually connected a toaster to the internet, and they had, you know, you could send it an SNMP packet and tell it how burned you wanted your toast. And that was a joke. But a few years later, somebody came up with a high-end refrigerator that is, in fact, internet-enabled. It has a nice touch-sensitive panel on the LCD display. You know, in addition to the usual paper and magnets that we use to communicate with family members on the front of the refrigerator, now we can do email and web pages and blogging. You can blog about your parents' you know, last egregious action against the, you know, juveniles in the home and all this other stuff. Another possibility, though, is that the things that you put inside the refrigerator might have RFID chips in them that identify them. So if you have an RFID detector in the refrigerator, it could figure out what it has inside, which means it could surf the net looking for recipes that it knows it could make based on what you have inside, and then give you a list of things for dinner or possible dinner menus when you get home, which sounds, you know, pretty cool, actually. You could extrapolate. You know, you could be on vacation and you get an email, and it's from your refrigerator. And it says, I don't know how much milk is left, but you put it in there 3 weeks ago, and it's going to crawl out on its own if you... Or alternatively, you might be shopping and your mobile goes off. It's an SMS from your refrigerator. Don't forget the marinara sauce. I have everything else I need for spaghetti dinner tonight. Now, it actually sounds like kind of an interesting, you know, future worldview. The Japanese have done a terrible thing to us, though. They have invented an internet-enabled bathroom scale. And you step on the scale, and it figures out which family member you are based on your weight, and it sends the information to the doctor, and it becomes part of your medical record, which is, well, you know, that's actually not so terrible, except for one thing: the refrigerator is on the same network. So when you come home, you see diet recipes coming up on the display. There are internet-enabled picture frames. And you can upload images, you know, from your digital cameras, put them in a server. The picture frame every 24 hours wakes up, downloads its instructions, throws some pictures away, cycles through others. And it's actually very nice because you just put these things in the living room, and the grandparents don't have to worry about booting up Windows or anything. They just turn the picture frame on and it does its thing. Those of you who are security-minded will appreciate that the website that it's downloading the images from needs to be protected, because otherwise the parents are going to see things they hope are not the grandchildren. So this says that security is just as important at home as it is in the office. And you see things that look like telephones, but they're really voice-over IP computers. But the guy in the middle is the one I like the most. He invented an internet-enabled surfboard. And I guess he was sitting out in the water in San Diego waiting, you know, for the next wave, thinking, you know, if I had a laptop and my surfboard, I could be surfing the internet while I'm waiting to, you know, surf the Pacific. So he put a laptop inside of his surfboard and stuck a Wi-Fi server in the radio in the rescue shack, and he sells this as a product now. So I predict. I remember earlier I had said that I thought there'd be more devices on the net than people. I really am convinced of that. And if you think of the number of appliances that you use every day at home, in the office, carry around on your body, and maybe in the car, there really could be a lot of internet-enabled things. Could be hundreds of them. And some of them that I've just mentioned are actually becoming part of the internet world. I don't have time to go through all of the examples here, but maybe the internet-enabled socks would be interesting. You know, when we send astronauts up, we put instrumented clothing on them. So it's keeping track of their vital signs, and that's important to us to make sure they're okay. You can imagine, what if all your clothes were internet-enabled? So I thought, well, okay, what if my socks were internet-enabled? What could I do? Well, let's see, I could send an SNMP query to the sock drawer, and I'd get back a report saying there's 17 matched pairs of socks, except sock number 144L is missing. So I'd send a multicast around the house, and you know, I'd get a report back, hello, this is sock 144L, I'm under the sofa in the living room. We've now solved the problem of the missing sock. Okay. Oh, well, wait, I should really say something about that. There are some fairly significant changes that are underway in the internet during 2008. One I already mentioned is the introduction of IPv6, but also domain names that are written in character sets other than Latin. So things that are written in Cyrillic and Chinese and Hindi and Japanese and so on, those other scripts are going to be introduced into the internet probably in the second half of 2008, assuming that ICANN manages to get all the pieces put together. There's still work going on to standardize the protocols that are required, and it's very tricky, very complicated stuff. But it's very important because a lot of people would like to be able to interact with the net using domain names that are written in languages other than those expressible in Latin. And the other thing which is important is the introduction of digitally signed domain name entries in the DNS lookup system, so that when you do a lookup to translate a domain name into an IP address, what comes back, if you ask for it, is a digitally signed entry that gives you some sense, strong sense, that the translation has not been altered since it was put in by whoever it is that owned that particular domain name and IP address. And so getting back a signed response is a way of removing at least some of the risk factors of phishing and farming, which are known attacks. Okay, oh gosh, we have so little time. What time do we actually, is this thing supposed to cut off 2 minutes ago, or?
Yeah.
Oh shoot.
Keep going.
Well, all right. Let me just, I want to take two other points, one about the interplanetary system and one about something I'm going to call bit rot. I have been trying to think in terms of 1,000 years, asking, okay, we've got this internet, data is pouring into this thing. What is going to happen 1,000 years from now? You know, what will it be like? Now, I can't even for a moment predict what the world will be like and how the technology will look, but I'm imagining that I'm surfing the internet. I do a Google search if we're still around, or whatever succeeds, and I get back a 1997 PowerPoint file. Now, I suppose I'm using Windows 3000 or something like that. The question is, will Windows 3000 know how to interpret a 1997 PowerPoint file? And the odds are pretty good that it will not. And this is not a dig at Microsoft. Even if you were using open source software and standards, having them maintain stability over 1,000 years seems like very unlikely. So now the question is, well, what is going to happen if over the course of time, as we accumulate more and more piles of bits that were meaningful at one time, will they lose their meaning because we don't know how to interpret the file formats or any of the other parts of them? And the answer is scary, because it could be that the generations further on won't have any idea what the hell we were doing, what we were like, because all the stuff about us is in formats that they don't know how to interpret. So the question is, how do I prevent that kind of bit rot? How do I maintain the ability to interpret bits? It's probably not enough to say, well, I'll translate them into the new formats, because in some cases you won't be able to do that. In some cases, the software won't be maintained anymore. And so you start to get into intellectual property problems of, gee, when they stop supporting this particular application package, should we insist that it becomes public domain so that other people will still be able to interpret old formats? What if you have to hang on to the operating system that ran the application that knew how to interpret the bits? What if you have to run a simulator of the computer that ran the operating system that ran the application that knew how to interpret the bits? Nobody has a good answer to this right now. And it is not simply open source. That is not the answer. So that's a big problem, and I think that's an area where you could potentially make a big contribution. Okay, interplanetary internet in 2 minutes. The system, the space exploration that we've been doing has mostly been based on the deep space network communicating with spacecraft over point-to-point radio links and sometimes over radio relays, sort of a bent pipe. The problem is that as time has gone on, as we put more elaborate systems in place, we've discovered that the point-to-point radio links are simply not sufficient to service the increasingly complex space exploration structures or architectures, nor is it adequate to deal with the multiplicity of these things. So today there are something like 30 or 40 different space applications in operation today, and the Deep Space Net that's run by JPL has got to schedule this point-to-point 70-meter dish to pick up the signals and translate the data and everything else. When the rovers first started to transmit data straight back to Earth, they discovered that the radio that was used was overheating. And so they had to reduce the duty cycle in order to keep it from damaging itself. And it was only a 28 kilobit radio anyhow. So now the scientists are sitting here saying, I can't get all my bits back. The guys at JPL reprogrammed a second radio which had 128 kilobit capacity, but it could only reach up to, the orbiting satellites. We had 3 or 4 satellites in orbit, so they reprogrammed everything to do store and forward. So they pushed the data up at 128 kilobits, store the data in the satellite. When it got around to the point where it could squirt the data at the Deep Space Net, it would do that. Well, that's store and forward. Guess what? That's how the internet works. So we thought, well, maybe we should deliberately design a networking protocol that would work in deep space. So we started out thinking, why don't we use TCP/IP? Well, that didn't last long. First problem was, gee, how do you do flow control? Well, you tell the other guy when you run out of room. Well, that's nice, except that the guy won't hear me for 20 minutes because Earth and Mars are that far apart when we're farthest apart in our orbits, and it's 40 minutes round trip time. So that doesn't work. And then there's this disruption problem. There's this thing called celestial motion, and you're talking to something on the surface, and then the planet rotates. And then you can't talk to it anymore until it comes back around again. This is not very friendly to the normal TCP expectation that you're connected. So we had to develop a whole new suite of protocols that we call delay and disruption tolerant networking protocols. Those have not been tested in deep space. They have been tested terrestrially, and they've been tested in tactical military communications, as well as a civilian application for the reindeer herders up in the northern part of Sweden, Norway, Finland, and Russia. The reindeer herders live in a place where they're so far north that the antennas that you would use for satellite communication are right on the horizon. And during the wintertime, they're really kind of disconnected from each other. So we did a test one summer using all-terrain vehicles with a laptop with a Wi-Fi capability and a Wi-Fi hotspot in the village. And you would sort of episodically wind up at the village, dump contents out using DTN, and then pick stuff up and then go off again. It was sort of like a data mule going from one place to the other, but it was all highly haphazard, not scheduled at all. And the protocols were able to support that mode of operation. That works also very well for very deep space environments. So we tested this terrestrially, and we are about to, believe me, in space exploration, about can mean anywhere from 2 to 3 to 5 years. We are hoping that around 2009 we will do some space testing of this stuff with the space station. And then around 2011, we're hoping to get access to the Deep Impact platform, which is still there, and upload our protocols and then run a deep space test with this thing. If it all works out well, these things will become standardized protocols that will be used for every mission that gets launched. We're working internationally with the Consultative Committee on Space Data Systems to standardize this protocol suite so that other international space platforms will be able to interwork. And what we hope will happen over time is that each time we launch a new mission, we'll actually add another piece of a deep space backbone that will support space exploration both in manned and unmanned missions. So that's the current state of affairs, and so we're hoping we'll see some significant progress during the second decade of the 21st century. Okay, so that's it. I'm happy to try to answer questions, and I know I kind of messed up by going on and on. This is what happens when a Stanford professor gets you trapped in a room, even an old one. Yes, sir?
Can video sync the internet?
No, it won't. And
well,
it will not.
That's clear.
And the reason I don't think it will is that we'll see different modes of use, like the use of broadcast delivery instead of point-to-point links delivering repeatedly. And we're also, we're seeing, even with YouTube right now, it's not syncing the net. I'm seeing already downloading of long 20-minute and 30-minute segments with very good quality that you play back after downloading. But the fact that you can download and play back relieves the network of a lot of its burden of trying to do things exactly in real time. And my sense right now is that with huge amounts of storage available, locally where you are, the ability to download either real time, faster than real time, or slower than real time makes it possible to pick and choose what you want to watch, assuming you've already got it stored. So I don't expect, the only place where it's a challenge is where it has to be real time, like video conferencing. And even there, the capacities of the backbone of the net are growing pretty rapidly. Next one. Yes, sir?
What happened to allow embarrassable governments to block certain sections of the internet?
I did not hear you say that.
What happened to allow embarrassable governments to block certain sections of the internet?
Okay, some governments do want to block. When you say block some sections of the internet, what I think you're really saying is block websites or something. I mean, we have to get at the right level of abstraction here. So yes, there are some governments, China is an example, that would like to limit access to people. It doesn't work very well. John Gilmore had that famous quote that censorship is interpreted by the internet as damage and it roots around it. It's a pretty good quote. The fact is that content comes from everywhere in the network. It gets replicated, and it's very, very hard to target one site and be assured that you've somehow constrained things. It's also very hard at very low levels in the net to figure out what's going on. So, for example, if you wanted to scrutinize every packet and say, aha, that packet has something in it I don't want the users to see, the first problem is you'd have to assemble the packets to figure out what the object is that they're looking at, because each packet doesn't have very much in it. And second, if you encrypted everything, it isn't clear that anybody could figure out what it was on an end-to-end basis. So I think it's very, very hard to do, although there will be attempts to do it. Yes, sir?
A legal lecture saying that certain providers and hosts are required by certain governments to block certain content because of their copyright laws. And if they don't, they get sued.
Yes, okay, so this is a different question. Now, this is where the government mandates the constraint on transport or showing of content. We experience this at Google. China tells us we cannot show certain answers to the searches in our network. We spent a year arguing whether we wanted to operate under those conditions, and we chose to do it in the end for two reasons. First of all, we believed that by providing the search capability, we would deliver more information to our Chinese colleagues than they would otherwise get. Second, the Chinese government agreed to let us say, when there was a response that they didn't want to show, we can actually say, we blocked this because we believe we are blocking it in conjunction with the Chinese government's need or demands. But we're allowed to say that, which means at least we tell them that something got blocked. And finally, the amount of material that's being blocked is de minimis in absolute terms. So could I also say that the Chinese government is not the only example of this. Germany and France do not permit the presentation of Holocaust materials or materials that deny the Holocaust or materials that people try to make money out of by selling artifacts and things like that. That's illegal too. So in every country in the world, we've found that there are constraints and restrictions. And if you want to operate there within the law, you do have to apply these things. But they're sort of voluntary. They're not down technical things down at the bottom. Yes, sir?
I guess you have to block it with the source, because once it's on the net, it's going to be around.
Actually, yes, that's right. And so each party that delivers information is the one that has. So all we can do is block the information about that site, but we can't stop somebody from actually going there. That's not in Google's case anyway. But you're right. You have to block at the source because, as you say, it comes from everywhere. Yes, sir.
Do you think net neutrality will be an issue in the future, or do you think carriers will reassert themselves?
It's the net neutrality question is a good one. It was very hot for about a year and a half. The issue here was whether or not the broadband providers were permitted to arbitrarily decide to somehow interfere with a consumer's ability to get to any application on the network. And there was some high rhetoric going back and forth for a while where one of the telcos said, well, we don't believe we have the obligation to allow our customers to get to every product and service on the internet. We're going to block that, or we're going to force the other side to pay us, or we won't deliver to this customer. Well, the customers are saying, wait a minute, you told me that you sold me access to the internet. That's all of the internet, not your part of it, not the part you wanted, or not the part that paid you to deliver to us. So there was legislation to try to codify that in law. It didn't pass, and it's probably just as well, because trying to write that into law is not so simple. It isn't dead yet, but most likely what will happen is that if it's recast at all, Congressman Markey is potential, and Snow and Dorgan on the Senate side, they may revise the language of it to speak more about non-discrimination with regard to the sources and sinks of traffic, rather than trying to say that all packets have to be equal, which is not what any of us in favor of net neutrality ever said, but our message was distorted that way. So I think the answer is there will be a lot of pressure to keep the network open, for the simple reason that if it isn't open, you will lose a huge amount of innovation and the economic benefits that come from it. And if we close the network down in the US, guess what? The rest of the people won't. So all the inventions will go over there. So I hope that we don't have that problem.
What about recent machinations by Rogers and Comcast?
Yeah. Pardon me while I get my blood pressure down. It was really quite interesting, because during the debates about possible legislation, the telcos and the carriers, the broadband cable companies said, oh, we would never, ever do any of the things that you are afraid we would do. Okay, so that's what they said. And then after the legislative hot potato died down, to mess up a metaphor, we found that Rogers Cable in Canada was injecting ads on top of other people's web pages. And you know, it's sort of like when you've seen on television when they're rolling the credits and they squeeze the screen down and they run the ad for the next program or something. It's a little bit like that, altering the XML. We had an instance where I think AT&T had blocked certain text messages that they thought were inappropriate. You know, excuse me, but there's this thing called the First Amendment right in the United States, and you don't have any right to interfere with that. We have seen a number of things. There was a much earlier event where a Madison Cable Company had deliberately blocked voice over IP. And we had another situation where Comcast was running the Sandvine. Let me make sure that I'm careful here. It is my understanding that Comcast used the Sandvine equipment to analyze the protocols that were in use on their broadband network. And when they detected BitTorrent, because they believed or had some reason to think that BitTorrent was unfairly consuming the capacity of the net, they would send out fake reset messages to each side of the BitTorrent exchange, leaving each party thinking the other had hung up. And they've characterized this as simply a delaying of the file transfer in order to manage the capacity of the net. And my thought is there are better ways of traffic shaping that don't require that kind of abrupt interference. Yes, sir, you had your hand up also.
I was just going to ask you how you found working with the DSN guys who don't believe in packet switching.
Well, that's a socio-political question. Right. The question is, how did I find working with the deep space network guys who don't believe in packet switching? It's been frustrating in a way, and yet, if you want to sell an idea, and there are people who resist it, you have to. That's your problem. You have to explain why it is that this is a better idea. And if you can't quantify the improvement, it's not an easy argument to make. And so I now have real data that I can show from a military test that was done in tactical communications, where the use of DTN compared to TCP/IP gave us 10 times as much capacity, because we didn't require a continuous connection between the source and the destination, whereas the standard techniques in the DSN require that there be a continuous link between the source and the destination. So I think we now have some concrete examples of why this is a better architecture. We think it also creates a lot more flexibility than you would otherwise have, particularly when you have sensor networks and self-organizing systems and large numbers of participating platforms in a space exploration experiment. Okay, I'm way over time here, so I don't know what to do about that. I don't mind. I'm having a great time if you are. Why don't we take 2 more, and then we'll have to call it quits. I saw a bunch of hands going up over here, but everybody wants to go home. Yes.
Just wanted to get your comments, thoughts on IPTV adoption in the U.S. It's been rather sluggish here compared to other continents. So what's your...
So yeah, the IPv6 adoption in the U.S. has been de minimis.
Right.
Part of the reason is that there's been a fair amount of IPv4 address space available. But also there hasn't been this demand coming from the, either the customers of the ISPs. I think that until companies like Google, for example, or others that have a significant presence in the internet service world start saying, I need this, I'm ordering this now, when can you supply it? Until that happens, there probably will be a kind of a sluggishness. The other parts of the world have already figured out that they don't want to run out of V4 address space. They don't want to have a situation where a large number of people have mobiles, for example, that have to be given IPv6 addresses that can't reach any of the services that are on the net. I'm hoping that there will be an awakening, and you can be sure that during 2008 and 2009 that there will be a lot of effort placed to remind people that they don't want to go through this a transition in an emergency way. They want to do this in a planned way. Okay, we have any more or not? One in the back. Yes, sir.
If I'm correct, multicast has been built into IPv4 for a long time. Why, in your opinion, has the adoption been so slow?
Actually, not only is it slow, but I think it probably may not be very widespread at all. 2 reasons. First of all, the original multicast design imagined that there were a group of people, each one of which could be a generator of content, a speaker, if you like. And in order to make that work, you had to build a multicast tree for each party. Okay, so you wound up having n multicast trees for each speaker, and the amount of data that had to be transmitted around and maintained turned out to be very unwieldy and didn't scale very well at all. Then the interest shifted over to single source multicast, which is simpler to implement. There's only 1 tree involved. But I believe what's happened is that it's another one of those alternative to this was to use caching at the edges of the net. And rather than having a multicast tree, just deliver the data from multiple sources close to where the recipients were. Akamai is a classical example of a commercial company that does that. We do similar kinds of things because we have a lot of cache capability scattered around in our data centers. So it just hasn't been, the need for it has not been forced on the applications that exist today. Now that might change over time, especially as we see more and more group kinds of interactions happening, more collaborative activities. You may see an increased demand for some form of multicast. Personally, I hope that if we end up with that demand, that we find a way to take advantage of naturally broadcast media in order to make the multicast easier to implement, because in some cases it's just a question of transmitting on that broadcast channel and everybody gets what you want. I think we got to cut this off now because other people need to do other things. Thank you so much for having me here. I appreciate it.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.